You've definitely got a bottle of this in your kitchen. But did you ever stop to think that the secret to vinegar's sharp kick is connected to the same chemistry that gives perfumes their sweet smell? It's pretty wild. Today, we're going to get to know the surprisingly versatile molecule behind it all.
So what is it? What's the secret ingredient that gives vinegar that unmistakable sharp tang? That powerful punch that makes pickles so great and a salad dressing really pop.
Well, it all comes down to this one tiny molecule, ethanoic acid. It's the star of the show. In fact, the vinegar in your cabinet is really just a simple solution of about 5 to 8% of this acid mixed in water. That's it.
Now, its proper chemical name is ethanoic acid, and its formula is CH3COOH. You'll also hear it called acetic acid pretty often. It belongs to a big family of compounds called carboxylic acids, and they all have one very special feature in common.
And right here, this is the most important part. See that COOH bed at the end? That's called the carboxyl group. Think of it as the business end of the molecule. It's what does all the heavy lifting. It gives ethanoic acid all its acidic powers and basically tells it how to interact with everything else. All right, so we know what it looks like, but how does this molecule actually behave out in the real world? Let's take a look at its physical properties. First things first, it plays really well with water. That same carboxyl group we were just talking about, it acts like a little magnet, forming super strong connections with water molecules. And that's why it dissolves so perfectly, letting us make things like, vinegar. Okay, so it mixes with liquid water. That makes sense. But what happens if you get it really, really cold? This is where ethanoic acid gets a little weird. Now check out these numbers. Acetic acid's melting point is 290 Kelvin. That's about 17 degrees Celsius, or 62 Fahrenheit. Now compare that to water, which freezes at 273 Kelvin, or ethanol, which has to get all the way down to 156 K. This means ethanoic acid freezes at a surprisingly mild temperature. We're talking about a cool room. It doesn't even need to be winter.
And because of this strange property, it got a really cool nickname. In colder labs or climates, pure ethanoic acid can literally freeze solid into these beautiful ice-like crystals. So chemists started calling it glacial acetic acid.
So that's how it behaves on its own. But let's be real. Chemistry is a team sport. The real fun begins when molecules start interacting. So what happens when ethanoic acid meets other chemicals? This is where we see its true personality come out.
First up, we've got a classic chemistry showdown. Acid meets base. We're going to see what happens when ethanoic acid comes up against sodium hydroxide, which is a very common, very strong base.
When you mix them, it's like they do a little dance and swap partners. The atoms all rearrange themselves to create two totally new, stable things. And what we get is a perfect neutralization reaction. The acid and base cancel each other out, and we're left with a salt, in this case, sodium acetate, and good old H2O, water. It's a fundamental rule of chemistry. Acid plus base equals salt plus water. Okay, for our next reaction, remember that baking soda volcano you probably made for a science fair? Well, this is the exact chemistry behind it. It's ethanoic acid, our vinegar, reacting with sodium bicarbonate, otherwise known as baking soda. So looking at the equation, you can see some familiar faces from last time. Yep, there's our salt, sodium acetate, and water again. But look at that new player at the very end, CO2, carbon dioxide, and that changes everything. That CO2 is the key. It's a gas, and when it's released all at once, you get that awesome fizz and bubble show. So the next time you see that classic volcano eruption, you'll know it's just millions of little carbon dioxide molecules making a break for it. All right, for our third and final reaction, we're going to mix our acid with an alcohol, specifically ethanol. And the result of this one, well, let's just say it's a lot sweeter than you'd expect. When ethanoic acid and ethanol react, they go through a process called esterification. They basically join forces to create a brand new kind of compound called an ester. And, just like before, a little molecule of water gets kicked out in the process. And here's the really cool part. Esters are famous for how they smell. We started with sharp, pungent vinegar, but after this one chemical reaction, we've created something that can smell fruity and sweet. It's a total transformation of scent. Okay, enough with the theory. That's the chemistry. But where do we actually see this stuff in our everyday lives? How do we put ethanoic acid and its reactions to work?
Well, obviously, we use it as vinegar to preserve foods like pickles. Its acidity is great for that. But that esterification reaction we just saw, that's a huge deal in the perfume and food industries for creating scents and flavors. And the salts it forms, like sodium acetate, have all sorts of industrial uses too.
All right, let's think back to that sweet-smelling ester for a second. We made it by combining an acid and an alcohol. But chemistry isn't always a one-way street. What do you think would happen if we tried to reverse the whole process? What if we took that ester and hit it with a base?
And the answer is yes, you totally can. The reverse process even has its own special name, saponification. This reaction literally breaks the ester apart, turning it right back into the alcohol it came from and a salt of the original acid. So why should you care about this reverse reaction? Why is it so important? Well, this process, saponification, is the fundamental chemical reaction that's used to make soap. But the science of how soap actually works its magic to get things clean? Well, that's a story for our next explainer.